So today we want to talk about moving sources of waves. That is, when the source of waves is in motion, some weird things are going to happen. So let's take a look. Here we have an airplane making some sound waves, and at the same time it's making those sound waves, it's moving to the right. And hopefully you see that these do not look like the same pattern that we saw when we had an object at rest that was making waves. We can see that on one side the waves get pushed together, and on the other side the waves spread apart. Here we have the plane moving even faster, and it's way more obvious that the waves in front of the plane are being compressed in terms of distance, and the waves behind the plane are even more spread out. So this is what it looks like when the plane is at rest, sitting on the tarmac, giving off noise. All the waves are symmetrically located. The actual word you want to know is concentric. Concentric meaning same center. That means all the waves have the same center point because each wave was made when the plane was in the same location. Remember, these are actually spheres, so technically they are concentric spheres of sound. Okay, the wavelength will be the same in all directions, and everybody will hear exactly the same frequency, okay, because of the symmetry. When we go back and look at this one again, we will realize that the wavelength and the frequency will not be the same for all observers. Somebody who is in the direction that the plane is traveling will see the wavelength get shorter and the frequency get higher. Someone who is on the other side sees a much bigger wavelength and a much smaller frequency. Here again, way more dramatic. We can see that the wavelength gets really short, which means the frequency is going to be really high. Here we see the wavelength being long, and that means the frequency is low. This is referred to as the Doppler effect. The Doppler effect refers to the apparent change in frequency that occurs to waves when the source of waves is in motion. With the Doppler effect, the frequency gets larger in the direction that the plane is moving, and the frequency becomes smaller in the direction it's moving away from. The wavelength on this side gets smaller, and the wavelength on this side gets larger. If we have a freeze frame of this, I think this would probably be the best one to draw, and if you can color code it, so much the better. So what you can see here is a series of tuning forks, and it represents a tuning fork that is moving to the right, just like the airplane was. The different colors represent where the tuning fork was when it made the wave. So you'll notice that this farthest out wave that is in red was created when the tuning fork was in this position. Once the wave is created, it spreads out equally from that starting location. It doesn't know that the tuning fork has moved, so its center point is the original location of the tuning fork. The next one in green was formed when the tuning fork was in this position. So the green circle is centered around the position of the green tuning fork. And so on. The blue was created here, the orange was created there, the violet was created there, and the tuning fork has not yet made a wave for the location depicted in black. If it did, if you wanted to put it, it would just be a small circle right there. All right, and those circles will continue to expand. So again, on this side, the wavelength is short. On this side, the wavelength is big. On this side, the frequency is high, and on this side, the frequency is low. All right? This is the frequency of the fork, the actual original frequency. This person is going to receive a frequency that is higher than the original. This person is going to receive a frequency that is smaller than the original. You can hear this whenever an object goes by you at a relatively high speed. So in this case, it is a fire truck from over in the United Kingdom. And you can hear the change in pitch that occurred when the fire truck went zooming by us. I don't know why the video did not actually play. Hopefully this one will play. This is a person riding a motorcycle past us, and you'll hear the Doppler effect as they go zooming by. And again, we're not seeing it, but if you listen, you hear that change in pitch as it's going from toward you to away from you. So as it zooms by you, you pick up that change in pitch. This was a car zooming by the observer, and again you heard the change in pitch of the car horn. I apologize that these videos aren't playing, but the important thing is the sound that you're hearing from them. Okay? So the observer on the side of the road is going to hear high frequency when the car is approaching and low frequency when it's receding away from them. All right? This doesn't just happen with sound light. This doesn't just happen with sound waves, it also happens with light waves. Okay, so with light, if the source of the light is moving away from you, the frequency will decrease. Okay, that's often termed a red shift because the color will shift toward the red end of the spectrum. If the source of the light is heading toward you, the frequency will increase, and that is called a blue shift. Okay, the mathematics of all this looks like this. Okay, let me explain. This is the frequency emitted. I called it a moment ago the frequency original. You can call it either thing. It doesn't matter what subscript you use. Just make sure you know that this term, the top term, is the original frequency that's being produced. Either the frequency of sound or the frequency of light. FR is the frequency received by somebody who is at rest as the thing goes whizzing past them, or is just moving toward them or moving away from them. Okay, down the bottom we have 1 plus or minus V. That V is the velocity of the object that is giving off the waves. The object could be the fire truck, the motorcycle, the car, the sun, whatever it happens to be that's giving off the waves. This bottom number is the velocity of the waves themselves. It might be the speed of light if you're looking at light waves, or it might be the speed of sound if you're looking at sound waves. So depending on the type of wave involved with our Doppler effect determines whether or not you make the bottom number light or sound, speed of light or the speed of sound. We have a plus or minus because there's two different scenarios. We use the minus when it's approaching us. We use the plus when it's moving away from us. Okay? So again, the plus is for when it's receding, moving away, and the minus is when it's coming towards us or approaching us. When you do this, your frequencies are going to be in hertz, and your speeds are going to be in meters per second. All right, we will practice some problems with Doppler in a few days. All right, so again, here's what it looks like. This side is the side where it's approaching us. And this is the side where it's receding. All right, so hopefully you're okay with the idea behind the Doppler effect. Again, it's the apparent change in frequency of sound or light caused by the motion of the source, the thing that's producing the sound or the light.